If you are taking AP Physics 1 this year, this is the start of the resource you're going to want in your back pocket. Welcome to Unit 1 Kinematics. So this video kicks off a complete chapter by chapter series covering every single concept on the AP Physics 1 syllabus. Our roadmap is simple. First, we'll break down the core theory for each unit, and then we'll transition into solving actual previous past year questions so you know exactly how to apply it. Right, so if you're looking for a structured way to score a 5, hit subscribe and let's get started. So welcome to our first chapter. This is kinematics. So let's understand what is kinematics, right? So physics begins with motion. The world is full of things changing place. So a ball rolls across a floor, a person walks along a road, a car speeds up, slows down, turns and stops. A stone falls. So physics can explain why. Before physics can explain why any of these things happen, it must first describe what is happening. Study of kinematics relates more with the what than the why. The first description is called kinematics. So kinematics, its definition would be this. Kinematics is a study of motion without yet studying the cause of motion. So it describes where an object is, how its position, where an object is, how its position changes, and how motion itself changes with time. So it does not begin by asking what force acts on the object. It begins with a more basic question. It asks, how is the object moving? And this distinction is something that we care about. So let's say you throw a ball upward. Kinematics describes how high it goes and how long it stays in the air and how its velocity changes and where it is at the moment. And dynamics which comes later, which asks why the ball behaves that way, the way it does. So we care about things like what force acts on it, what mass it has, or what gravity, or how gravity changes its motion, right? So the kinematics part usually deals with the how. The kinematics deals with the how of things, whereas dynamics would generally deals with the what. Okay. Now, let's understand the language of motion before we get deeper into the concepts. So motion, since we're talking about motion is nothing but change of position with respect to time. Okay, what do we mean by this? If an object is said to be in motion when its position changes with time. What do we understand by this? So this is such a simple statement, but then this would become the whole foundation of kinematics. So there are already two ideas present here. One is position and the other one would be time. Position and time. So position tells where the object is. right? And time tells us when the object is there. So motion is a relationship between these two things, position and time, where the object is and when it is there. Okay, so let's say you have a car parked in a position. So I'm gonna have a car. So it's just parked somewhere. And this car has a position. It's parked, it's not moving, it's in one place. But if that position does not change as time passes, the car is at rest relative to the ground, right? So if it's not moving, then you say it is at rest relative to the ground. Let's say, so this is at rest. Now I assume that my car is exhibiting some kind of movement. It's moving in this direction. So this moving car, the position of this moving car is changing from moment to moment. Position is changing moment to moment. And kinematics studies that change. So motion does not mean an object being somewhere. It is more of a pattern of position across time. So a single photograph of time, of a car, tells us where the car is at one instant, right? So if I have a picture with a car in it, you can tell where the car was at that particular instant. And let's say I show you a video of a car moving, and that would tell you how the position changes. So kinematics is closer to the video than to the photograph. You care about how it's moving. You are concerned with the sequence. And what do we mean by that? You ask, where is the object at T1? You ask, where is the object at T2? You ask, where is the object at T3? So from that sequence, physics can build the idea of displacement, velocity, acceleration, graphs, and equations. So these things, we will deal with these things later. For now, the essential idea is you want to keep one thing in mind, that is, motion means, the only idea is motion means position changing with time. Okay. Next idea, the object model. Before you get into kinematics, before you start doing your projectile motion and everything, you want to understand the object model. What do we mean by that? So you are treating the object as a point. The object as a point. Well, in real life, objects have size. Let's say I am taking an example of a textbook as an object. So this textbook, let's draw a textbook. So this textbook would have things like size. This is my object, and it would have things like size, shape, color, texture, rotation. You can rotate them. You can talk about the internal structure and its vibration, right? So if you take any object, you're not gonna it's pretty difficult to look past these things, because an object obviously has its own things that makes it unique. A car would have wheels and doors. If your object is a person, they would have arms and legs. A ball can spin while moving. So these are properties an object would hold. But when we deal with kinematics, we begin by simplifying everything. And how do we do that? Very often, the object is treated as if all of its motion is represented by a single point. So instead of drawing a car or a textbook or a person every single time, I would simply represent it using a single point. Right? So this little point is called the object model or a particle model. We ignore the properties of this object. We ignore the size, we ignore the shape of the object, and track one representative point, usually its center. So this would be the center of mass, or simply its location. So this does not mean the object literally becomes a point. It means that for the question being asked, the details of the shape and the internal structure are not important. Right, so for the question we deal with, we don't care about the shape, size, rotation, vibration, etc. So we're gonna, call this a point object. You're gonna represent this by an object model, a particle model. Let me give you an example. Let's say you have a car, and that travels from one town to another. We usually do not care where the front bumper is compared to the back bumper. We describe the car's location as a whole. And if a ball is thrown through the air, we only care about its path. We can often treat the ball as a point moving through space. So this is one of the advantages. I would say it does not try to describe every single detail at once. It chooses the details that matters for the problem. So in kinematics, the first model is often this. You are taking a real object and then you are representing it as a point object. So as time passes, so that point has a position, right? So this now, instead of drawing a car, I would simply represent it using a point. Now, this point has a position. So as time passes, the position might change. So this might be at t equals 1. And at t equal to 2, my position could be somewhere here. So as time passes, the position might change, and if you try to study that change, then that would be kinematics. Okay, next, let's talk about references. Okay, now, motion is never described in complete emptiness. To say that an object moves, we must have some way of measuring it, right? So you cannot simply you cannot simply describe it in without a reference point. Let me explain this. So this you cannot put it in an emptiness, in complete emptiness. You cannot put stuff in emptiness. So things require something called a reference frame. A reference frame. So a reference frame is the point of view or measuring system from which motion is described. It's the point of view or a measuring system. All right. In ordinary AP physics problems, this often means choosing the ground as a reference frame. So a person standing beside a road sees a car moving past. So from the ground's frame, the car is in motion, right? But now imagine a passenger sitting inside the car. Relative to the car seat, the passenger may be at rest. So relative to the ground, the passenger is moving. So both statements can be correct if they are made from the different frames of reference. So from the ground, let's say there's a road, and there is the car that's moving, and there is a person. So he's in the ground, and there's a road, and that's the car is moving. So from his perspective, from his POV, from his POV, the car is moving, right? Now let's look at the person inside the car. To him, the car is not moving because he's inside the car. So the point of view matters. That's why the reference frame matters. Here it is the ground, here it is inside the car. All right. So both statements can be correct because they're made from different frames of reference. So you cannot say that the truth value depends on which point of view you're talking from. So if you're standing on the ground, then you can say that the car is moving, but if you're inside the car, then you can say that you're not moving. Both things are true. Why? Because they are made from different points of reference. So it's not just the property of the object alone. So it's not just the property of the object alone. It is the relationship between the objects and the frame which is observed. So a clean way to say this is to describe motion, we must say motion relative to what? So you are always, to describe it, you ask motion relative to what? Right? And that would be some kind of reference, frame of reference. So in the early part of kinematics, right, we usually choose a simple reference frame and we keep it fixed. Later, when we study relative motion, we compare what different observers measure. So I am trying to clarify these things in this video so that in the upcoming videos you're not too confused with when you do relative motion, you're not overly concerned with the why of things, and that's why I want to clarify everything in the first video. Okay. So for now, the important point is that every motion describes the description of every motion needs a measuring background, right? It would need an origin. It would need a direction and a clock. So in order to describe any movement, any motion, you would need these things. Now, I want to explain why. I want to explain the need for origin, the direction, and the clock. But let's get started with the origin. Origin. So an origin, what is an origin? An origin is where measurement begins. Okay, to describe position, we need a starting point of measurement. So you need to start somewhere. So you need a point, and that starting point is called origin. So on a number line, so let's draw a number line. You have 0, 1, 2, 3, 4, 5. So 0, if I say x is equal to 0, then I say my object is at the origin. So the object at x is equal to 0 means that it is at the origin. So this is a regular number line. But an actual number line has both positive and negative sides. You have 0, 1, 2, 3, 4, 5. -1, -2, -3, -4. So the object to the right of the origin is the positive position. If I were to put my object on, let's say 3. Oops. Okay, so this would be the positive position. And if I were to put my object on the negative side, to the left, then it might have a negative position. And this 0 right here is the origin. This is the starting point. So now you might have a question. You might ask, what is the positive and negative signs that we're dealing with all of a sudden? The signs do not mean good or bad, large or small, fast or slow. They simply tell the location relative to the chosen origin, right? They simply tell. We're not concerned with the fast or slow here. We are talking about the direction with respect to the origin. So imagine a straight road with a lamppost, and I'm going to choose that as my origin. So let's say you have a lamppost, and this is going to be my origin. And I'm going to call it 0. So if the east is chosen as positive, so let's say I'm going to choose this as positive. East is chosen as positive direction. Then a car at 20. So let's say I put my car somewhere here. This is at 20 meters. So if east is chosen as positive direction, then a car 20 meters east to the lamppost may have the position. So this, I would describe the position of this this object. This would have you chosen. Let's say this is a car. The position would be x is equal to 20 meters. Let's be more specific. X is equal to plus 20 meters. Let's say I put my car to the other end. I put my car to the west, let's say, at 20 meters. So I'm going to choose this as negative. Then the position of my car is negative 20 meters. So the signs here represents the coordinate system. So whatever thing you choose becomes the origin, and wherever the position is with respect to that origin becomes the coordinate system, the position. So the signs, they come from the coordinate system. So the coordinate system is mostly chosen by us. We choose it. So why is this important? So a coordinate system is not something nature does not have this. Okay, nature does not write lamppost x is equal to 0 on the road. It doesn't do that. It is a human measuring structure placed on the physical situation so that the motion can be described mathematically. So we chose this. So we have chosen a way to measure this. Next up, let's understand direction. So direction would be motion along a chosen axis. So in one-dimensional kinematics, motion happens along a line. Now we have dimensions, right? So if it's happening in a line, then you call it one dimension. So in one-dimensional kinematics, motion happens along a line. Okay, it was just moving in one direction like this. Motion happens in a line. Then I call it 1D. So the line, so when we think of a line could be horizontal, it could be vertical, it could be slanted, but the motion is treated as occurring along one axis. So it could take any path, but you would consider it occurring along one axis, right? Perfect. So this axis needs a positive direction. So for let's take an example of the horizontal motion. So for horizontal motion, we may choose the right as positive. This could be positive. This could be negative. And for vertical motion, again, we may choose the upward as positive, and then we could choose the downward as negative. So another person could choose differently. So let's say my friend comes along and she claims, nope, I'm going to take this horizontal motion, and then I'm going to take the left as negative and positive, and right as negative. And that is completely justified. You could choose either ways. It's absolutely fine. But yeah, because these are things that we assign, right? So they could choose left as positive and right as negative. The whatever thing you choose, the physics would remain the same, but the signs in the equation would change. You would not have the same, you might not get the same signs since you're choosing a different axis altogether, since you're choosing different directions for your motion, but the physics remains the same. So that's why the signs in kinematics is not random. They come from a chosen coordinate direction. So in one-dimensional motion, vectors are, now I will talk about vectors and scalars in the future if you are not already aware of it. But vectors, would, if I were to put it, if I have to give you a TLDR, then vectors are something that would have both magnitude and direction. Scalars just do not carry any direction, they are just magnitude. They just have magnitude. So in one dimension, vectors can be represented using plus and minus signs to indicate direction, while if you are talking about scalars, then you don't have to worry too much about the direction. So you don't ask, is this negative because it's wrong? No, you mostly ask, which direction did I choose as positive, right? So that's why you don't really confuse with the signs, because the signs are dependent on the conventions that you choose. All right, now let's move on and understand clocks. The clock. Motion in time. So position alone is not enough to describe motion. We also need time, as we discussed before. So if a car is at x is equal to 0 meters, then this tells us where it is, right? This tells us about the where, the position. But if later, if it becomes x equals 20 meters, then that tells us that its position is changed. Position is changed. Okay, but to describe the motion properly, we need to know how much time passed between those positions, right? We know something has changed. We know the position has changed. It has gone from x is equal to 0 to x is equal to 20. But we need to know how much time has passed between these positions. So the difference between moving, let's say I'm going to assume that the time taken was 2 seconds, right? So the difference between moving 20 meters in 2 seconds and let's say I have another example where it's moving in 20 seconds, 2 seconds and 20 seconds. The difference between these two numbers, these two values it's enormous, it's huge. The starting and the ending positions might be the same, but the motion is different. Do you understand? So you are still starting at x is equal to 0 and still ending at x is equal to 20 meters, but the catch is, if you're doing it in 2 seconds, it's different. If you're doing it in 20 seconds, it's different. It's completely different. So we need to know, that's why time is very important, because we need to know how much time passed between those positions. Okay. So kinematics always links position with time. The basic form of motion description, so this is how we describe motion. The basic form of motion description would be this. Now, what does this notation represent? This notation means that position, you call it position, as a function of time. So what does it tell us? It tells us that the position x depends on t. So you don't need advanced calculus, but then you need to know some basic algebra to deal with these things. So if you know how, but you should understand the idea that if you know how the position changes with time, you basically know how it's moving. For example, I have x is equal to 5t. Ooh, this requires some calculus, but okay. So if you were to differentiate this, so this describes the position that changes or increases steadily with time. And let's say I have x is equal to 2t squared, then this would describe the position that changes more rapidly as time passes. So yeah, so this is a compact description of motion overall. So now let's understand kinematics as a language with several forms. And then we'll try to understand a little bit about position, velocity, and acceleration. Yes, a basic review of everything that we will see in the upcoming videos. So kinematics is a language with several forms. What do we understand by this? So motion can be described in several ways. A student must learn how to move between them. You want to know how are they usually, described. So emotion can be described in words. So let's do a little mind map. So let's say I have the description, the language for it. This could happen in several ways, right? So you could describe these things in words. You could describe these things with a diagram. You could describe it with a table. Or you could describe it with an equation. What do we understand by this? Okay, so let's say something is moving and you want to describe it in words. You would say object starts from rest and speeds up to the right. So that's just using plain words. Now, if you were to describe them with a diagram, then it could be described like this. So this would be where the spacing between the dots would show how the motion changes. Now, if you were to describe with a table, I have two columns. So one represents the time and the other one would represent the position. The time, you are measuring it in seconds, let's say, and the position, you're measuring it in meters, let's say. Now, at 0, the position of the object is at 0 meters, and at 1 second it's at 2 meters, and let's say at 2 seconds it's at 4 meters, and at 3 seconds it's at 6 meters. So this can be described with a graph as well. Let's say I have my graph. I'm gonna call this x and t. If I were to try and plot this, I would get a straight line. This would be my graph. So this is a position time graph, obviously. So it can be described with an equation. So the equation to describe this whole thing would be x is equal to x naught plus vt. And these are not separate topics in the deepest sense, but they're all different languages of the same motion. So this would be representing it in an equation. These are different representations of kinematics. So you should be able to translate the words into diagrams, into table, into equations, and that into graph. So next up we have mostly covered everything with respect to the things you need to know before you actually start your kinematics. So we will, I'm going to end the video here, but then in the next video, I'm going to go a bit more detail into the dynamics, the what of things. And then after that, we will slowly get into the topics, and then we will understand the formula and everything. Thank you very much for watching.